I'm Brent with TechToolSupply.com. Today I want to show you how to do a basic RF distribution system using the frequency range of 5 to 1,000 megahertz. Now, there's a lot of variables that come into play when you're doing RF distribution. Today I'm only going to go over the very basic aspects of RF distribution. Now, one of the most important things you need to know when you're doing RF distribution is what's your source and what's the frequency range of your source. Most cable TV, off-air signals, and SMAT systems all use a frequency range of 5 to 1,000 megahertz. So if you're using one of those systems, you want to make sure that any device you get, amplifiers, attenuators, splitters, they all have a frequency range on them of 5 to 1,000 megahertz. Now, you are going to find some components out there don't have that broad of a range. And it may work, it still may work for your system. For example, if you have a cable system and maybe your cable company only uses the ranges of 10 megahertz to 700 megahertz, and there's a distribution amplifier that covers the range of 5 to 800 megahertz. Long as your source falls within the range of that amplifier or whatever component it is, you're okay and it'll work. I would recommend shooting for 5 to 1,000 megahertz only because as technology changes, companies are going to start using more and more of that range. Now, one of the common misconceptions that I want to squash is that splitters split signal. That's not the case. Splitters actually have a predefined insertion loss on them, which is a dB rating or decibel rating. And what the insertion loss refers to is how much signal loss there is between the input and the output of that component. For example, a two-way splitter has a 3.5 dB insertion loss on it. What this means, when put into an example, if you have 10 dB coming in from the cable company to the input of a two-way splitter, which again has a 3.5 dB insertion loss on it, the output of that, those two outputs, both are going to have a 6.5 dB output, which 10 minus 3.5 is 6.5. So any splitter that you look at, whatever that insertion loss is on it, for example, if we have an 8-way splitter with a 12.5 dB loss on it, that applies to the loss between the input and all 8 of the outputs on it. So this is a very important thing to remember, and this is kind of the sets the groundwork for all RF distribution. Now, it's all just addition and subtraction when you're doing RF distribution. It's just knowing what the values mean and making sure you take into consideration every variable. Now, another variable that's commonly overlooked is cable. RG6 cable, for example, over 100 foot has 6.54 dB loss at 1,000 megahertz. Now, when I say at 1,000 megahertz, I say that because it's different at every frequency. The higher the frequency, the more loss there is on the cable. Splitters are the same way. When you look at the insertion loss on a splitter, that is a typical insertion loss. And if you went to your manufacturer's website and you looked at the spec sheet for that splitter, you're going to see that at different frequencies that insertion loss changes. Same thing with RG6. At 5 megahertz and 1,000 megahertz, there's a huge difference. If we take a 100-foot piece of RG6 and we look at 5 megahertz at 100 feet, there's only less than half dB loss, where at 1,000 megahertz there's 6 dB loss. So between those two frequencies, there's a difference of 6 dB. Now this can cause all kinds of complications when you're doing larger RF distribution systems. It's commonly known as tilt, but today we're just going to go over the basics, and we'll discuss tilt another day. Now, when I design my systems, I like to design them with the higher frequencies, which means higher loss. The reason that I like to do that is when my system is completely designed, I would much rather have a signal that is too high than a signal that is too low. It's much easier to fix a system that has too much signal than a system that doesn't have enough signal. Now, there's two main kinds of systems that are commonly used in RF distribution. One is a home run system. Now, a home run system takes multiple TV locations all to the main source. For example, if we have 30 TVs, there would be 30 wires coming from every one of those TVs to our distribution point. Now, this is more popular in homes and small businesses, places where the distance between your source and your TVs is not too long, or there's not too many drops. Now the other type of system is a tap system. Now tap systems are more commonly used in big commercial applications, hospitals, assisted living. Actually, a tap system is what most cable companies use. Now the way that a tap system works is you have one main trunk line, and that trunk line goes along, and when you have a TV location, they put a tap in at that point, and then the TVs connect to that tap. Then on the output of that tap, the trunk line continues on until your next TV, they branch off again. That is a much more complicated system, and we're going to save that for another video as well. Now I'm going to show you a basic home run RF distribution system, and the little system we're going to design here we'll say has 16 TVs. Now on a 16 TV basic home run distribution system, we'll use our example source as a cable company. And to run to our 16 TVs, we're going to use a 2-way and 2 8-ways. Now in this case, the distance of wire between the 2-way and the 8-ways is only going to be a couple of feet, so we don't have to worry about calculating the loss on them. Now the 2-way has a 3.5 dB loss on it. As we said before, you want to look at your manufacturer's spec sheet and find out the insertion loss, or look on the front of the splitter to get that. Off of the 2-way here, we're going to take a couple of 8-ways. And again, we said the 8-ways here have a 12 dB loss on them. Now, to calculate the loss between the 2-way, the input of the 2-way, and the output of the 8-ways, we're going to just add these two numbers together, 12 dB and 3.5 dB. This will give us the total amount of insertion loss between the input of the 2-way and the output of the 8, which in this case the value is 15.5 dB. Now the next thing we have to calculate on this is the wire. Let's say that the wire coming off our splitters here is 75 feet. RG6 is different depending on whose wire you're using or who the manufacturer makes it, which model they're using. They all have different losses on them. You need to look at the manufacturer spec sheet, and they will have a section there which shows you over 100 feet how much loss there is at 1,000 megahertz. In this case, the cable that we're using has 6.54 dB loss at 1,000 megahertz over 100 feet. So to calculate 75 feet, we're just going to multiply 6.54 times 0.75, which gives us 4.91. And that right there would be our loss over 75 feet would be 4.91 dB. So now to calculate how much loss we have total between our TV here and the input of our 2-way splitter, we're going to add these two numbers together. So 15.5 plus 4.91 is going to give us 20.41 dB. So the total loss between the input of our 2-way and our TV here is going to be 20.41 dB. Now we need to calculate what signal level we want at the TV. Most guys engineering systems shoot for 5 dB. It's relative, but I would say 5 dB is a safe number to shoot for. So we're going to add 5 dB onto this 20.41. 5 dB plus 20.41, 25.41 dB. So 25.41 dB is the total signal that we need going to the input of this 2-way to give us 5 dB at our TV. Again, just to go through this real quick, 3.5 dB plus the 12 dB gives us our insertion loss between the input of the 2-way splitter and the output of the 8-way splitter. To calculate the loss of the 75-foot run here, we multiplied our loss over 100 feet at 1,000 megahertz times 0.75, which 6.94 or 6.54 times 0.75 gave us the 4.91. We add that to the 15.5, which gives us the 20.41. That's the loss between the input of the 2-way and the TV. we said that we want to have 5 dB at our TV, so we added another 5 dB onto that 20.41, which is 25.41. So when we put 25.41 dB signal into the input of our two-way splitter here, it's going to give us 5 dB at that TV. So now we need to calculate what we need to do from our cable company to make sure we have 25.41 dB at the input of our two-way splitter. Now let's say in this case that our cable company is supplying us with 6 dB of signal. So in order for us to figure out how much signal we need to go into the amplifier, we need to take 25.41 and subtract the 6 dB from it. So that would give us 19.41 dB. So that gives us the gain of the amplifier that we need to have to put in place here. So what I'm going to recommend in this case is that we get a 30 dB amplifier which has a 10 dB adjustable gain on it. Now what that means is that the amplifier can go as low as 20 dB gain up to 30 dB gain. So again, I always design things a little bit hot so I have a little bit of room to move. So for example, if wherever one of these TVs was at, somebody was putting a second TV or something that required a second signal, we have a little bit of room to move on the amplifier. So we're going to put a 30 dB amplifier in here with again, it has 10 dB gain adjustment, so this can technically be adjusted anywhere from 20 to 30 dB. So if we adjusted this down to 20 dB, and again, this is gain. So whatever you have coming into this amplifier, gain means it's going to add this amount of signal on top of it. So if we have 6 dB coming from the cable company, and we have the amplifier adjusted to 20 dB, on the output of it, we would have 26 dB, which is about half a dB more than what we calculated we need at the input of the amplifier of 25.41. So just to go through our completed system, we have 6 dB coming in from the cable company. That's hitting our amplifier, which has 20 dB of gain. So we have an output of 26 dB on the output of our amplifier going into the input of our two-way splitter here. So our two-way splitter is going to have 3.5 dB of loss, which is going to knock our 26 dB signal down to 22.5 dB. Then that's going to come along here. It's going to hit our 12 dB or our 8-way, which has 12 dB insertion loss on it. So after our 22.5 dB hits our 12 dB, we're going to have 10.5 dB on the output of the 8-way, and then we have a 4.91 loss over 75 foot of RG6 hitting our TV. So our NTV is going to have just over 5 dB of signal, just like we planned. Now, when you're doing RF distribution, and I say this pretty much in every video that I've done about RF distribution, you want to get a signal meter. And I keep saying this because there's a lot of guys out there that don't think they need them. You do. If you don't have a signal meter and you're doing RF distribution, you're blindly adjusting things and you really can't see what you're doing. In a case like this, you would want a signal meter here to know what your cable company is supplying you with. You want a signal meter here so you can adjust the output of your amplifier. And of course, when you're all done, you want to be able to verify the signal that you have at the end. And that's just using it for the installation of the system. When you have to go out and troubleshoot a system, and you don't have signal at the end, you want to be able to start at the cable company, measure here, measure here, measure here, start going through the system and find out where you're losing the signal at. If you have a signal meter, it's going to take you half an hour. If you don't have a signal meter, you're going to have to go through and replace wire, replace cable, until you figure out what the problem is. And again, I know I sound like a broken record, but I was a guy in the field that for the longest time believed that I didn't need a signal meter. And once I had a signal meter, it was like putting on glasses for the first time. I mean, finally can see everything. So this is a basic RF distribution system. The concepts here, I mean, you can do systems 10 times the size with just these basic calculations here. So hopefully this helped you out. Come visit us at techtoolsupply.com for more videos.